All right, let's get started. So chapter 6 now is largely focused on applications of integrals. What can we use integrals to solve? See, we kind of lied to you a little bit in the beginning. I said integrals give you areas, right? And we use that to guide our intuition. Then we came up with the exact definition of an integral. And then we said, okay, now you can use an integral to calculate an area, right? An integral is not an area. An integral is an infinite sum where you have a function times some really small interval, right?
Yeah.
That's what an integral is. We can use integrals to calculate areas. And we found out we can also use integrals to calculate changes in positions from velocities, or changes in velocities from accelerations, right? It doesn't just give us an area. So what is an integral? Let's write it out, the exact definition really quick. It's the limit as our partition gap goes to 0 of a sum from k equals 1 to n of some function at a value in the interval times the width of the interval, where the width of the interval goes to 0.
Yeah.
Right? That's what an integral is. And if we think about this as the height, so if I've got some area I want to calculate, here's some area. We'll say it intersects here at the point A. We'll say, keep this up. Try to keep it a one-to-one function. Pretend it's a one-to-one function. And that's some point B. And we can think about this as y equal to f of x. Here's our function, right?
Yeah.
Then one way that I could calculate this area is I could use a bunch of infinite rectangles. So my y now gives me the height of this function, right? So for some rectangle, here's an arbitrary rectangle. My width here is delta x sub k, and my height of this rectangle is f of c sub k. And if I do infinitely many of those rectangles across this whole thing and add them up, that's what an integral is. It gives me an infinite sum. So one way that I could calculate this integral is calculate this area is I could say it's the integral from 0 to a, we start at 0, go to a, of the height times the width. My height is f of c sub k, or I'll just call it y sub k, my y point there,
Yeah.
times dx. Right? That's the integral I would use.
I mean, yeah.
Dx is a stand-in for all these little widths.
Okay.
In the limit, these widths go to dx. Is one way that you can think about this. So how do we think about an integral intuitively? This is an infinite sum of some value times an infinitesimally small width. It's an infinite sum of those.
Yeah.
From 0 to a. Right? That's one way I can calculate this area. How else can I calculate this area? I could have just as easily thought about my rectangles this way. And added them all up this way, right? I could have done that, a bunch of rectangles this way. So let's rethink about it. If I know that y is some function of x, I could just solve this, whatever this expression is. It's going to be something like y equals x squared plus 2 or something like that, right? Some function of x. I can always solve that thing for x and get a function of y. So I can also call this x is equal to some function in terms of y. You plug in a y, it gives me an x, rather than you plug in an x, it gives me a y.
Yeah.
You see that? So this width right here is always what? It's just y for our function there. Our width here is always my x coordinate, right? For this point, this is at xy. This distance right here is always just x. So wherever the x is. This distance is always just x. This distance is always just x. Plug in your y, you figure out what the x is, right?
X sub k or just x?
Just x. I should have just said y here. So going back, well, we can have both of them up here at the same time. So we'll use the same point in both these. Something like that. This point right here is a point xy, right?
Yeah.
Now, I can think about this as some small change in x, and I can think about this as some small change in y, right? So if I use a bunch of rectangles this way, then I'm going to be doing a sum. Doesn't matter what our bounds are for now. But the point is I'm going to be doing a sum of a bunch of x's times delta y's or I could be doing a sum of a bunch of y's times delta x's. Either way. So I could calculate this integral as the integral from 0 to a of y times dx, which is the same thing as, here's the way you're used to seeing it. This is saying the exact same thing, f of x times dx, right?
Isn't that just equal to 0?
Oh, sorry, I meant to put 0 down here. Thank you. That's a 0, not a. But if I give you a function, you typically know how to calculate this, right? This is saying the exact same thing as that. I could also calculate this area going from 0 to b of x dy. And that's doing it this way.
Yeah.
That's two different ways of getting areas. Now, we also used integrals to calculate velocities, right? If I've got some velocity function, or not calculate velocities, calculate changes in position from velocity. If I've got some velocity function, there it is, and I want to know the change in velocity from some point A to some point B, not the change in velocity, I want to know how much displacement there is from some point A to some point B. How do we calculate that? I say the change in position from A to B is the velocity function times a little bit of time, and add those up. It's an infinite sum of velocities times times, and add all those up, and that gives you your total displacement from A to B.
Yeah.
Right? A velocity times a time gives you displacement, right? Makes perfect sense. So now, we know how to calculate an area. An area would be when I'm doing my integral, I'm doing a height times some small width, dx, dy, doesn't matter. Velocities, if I want to calculate change in position, it's going to be a velocity times some small change in time, dt. What about a volume? How would I calculate a volume using an integral? I need to get an area function in terms of x, and multiply it by dx. If I do an area times a small width, that gives me a volume.
You're saying, like, take the area and then.
So,
I'm a little lost.
yeah.
You know your bounds.
The same way that you always know your bounds. Just because I didn't write it in, from A to B, that's fine. As your x varies from A to B. Sure. So, let's draw some picture and get a feel for how this might look. And I'm going to use it so that we have a dy rather than a dx, but give you the general idea. The problem is we're going to have to draw 3D, and I'm terrible at drawing 3D. So you're going to have to really exert your imagination here for a second. But imagine that we have some, here's the top of this figure, some weird figure, and then it comes straight down. That's not straight at all. Straight down, and then here's the bottom of the figure. And we can't see those. You with me a little bit?
Yeah.
You can kind of see it. Here's the top, and then it just goes down, and it's sitting on the ground. So it's got straight up edges. The top looks the exact same as the bottom.
Okay. So you just find the area of the top times the height, right?
The area of the top times the height is a straightforward way to do it, right?
Okay.
But you've got the perfect idea. You take the area of the top and you multiply it by the height, and that gives you the volume. Okay? Now imagine that the volume is no longer straight edges anymore, but that these curve in like that and then come back out. Okay, now how do we do it? Now we're in trouble, right?
Yeah.
So I'm going to try and put this on an XY grid, and it's going to look awful, but we'll try it. So here's my X. Here's my X going this way, so it's sitting on the XY plane. Here's my Y. Oh, wait, am I doing that weird? Here's my X. Here's my Y. Here's my Z. You with me?
Yeah.
Yeah.
And we're saying that this thing, it starts at Z equal to 0 and goes up to Z equal to A. So we'll pretend the height of this thing is A. So it's going from Z equal to 0 to A for the total height.
Okay.
And it's sitting flat on the XY plane, even though my picture might not make it look that way. Okay, how can we calculate the volume of this thing? In general, here's what we're going to do. We first need to come up with a function to calculate the cross-sectional area of this thing at any given point. I need to be able to calculate the cross-sectional area here, 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 here. So for any point, Z, for some arbitrary little z, I need to be able to calculate this z here. Just remember, this is the z-axis. For any z you give me, I need to be able to calculate the cross-sectional area at that point, right?
Yeah.
Pretend that this is a function that we know how to do that with. Well, if I take that z, that height at z, and I multiply it by a really, really small width, so now it's like a thin little shell out of that thing. You with me?
Okay.
So what is that going to be? If I have some area function that I know how to calculate the area when you plug in a z, then the volume of that little slab is going to be a times z times delta z, right?
Okay.
Of that little slab. Now to get the volume of the whole thing, I'm going to add up all those slabs. And the more slabs I make, the better approximation I get. And so to calculate the volume of this thing, we're going to be doing the integral from 0 to a of the cross-sectional area at z times dz. I'm going to be integrating as z varies from 0 to a, the cross-sectional area function times a small change in z. You with me?
Yeah.
Okay. That's the big picture of what we're going to be doing first. So let's do some concrete examples and actually see this in action, and then hopefully with that it will all come together.
Okay.
And this is going to be one of those classes where now we just do tons of examples. Quick definition. Now we have a definition for volume. The volume of a solid of an integrable cross-sectional area, a of x, from x equal to a to b. So if I have some area function x that I know is valid from x equal a to b, then by definition, volume is equal to the integral from a to b of a of x dx, which is what I just tried to give you intuition for here with this picture.
So do we already know what a of x is, or do we have to find the area first?
You're going to be given the a of x function, the area function, or you're going to have to come up with a way to calculate it. You'll be able to figure out what the area function is. The same way that when we were calculating this volume, or this area over here, the only way you could actually do that is if you knew what this function was, or had some way to calculate the function. Same thing.
Okay.
So yeah, you'll be given scenarios where you know how to figure out a cross-sectional area. Because you all know the area of a circle now, right? Pi r squared. Good job. We proved that that's the area of a circle.
We did?
Do we need to prove it real quick?
It would be helpful.
All right, let's do the area of a circle. What is the defining feature of a circle?
It's circular.
All the points are equidistant from the center,
Yeah.
right? So if I look at all the points x, y, such that their distance is a away from the center, that's the same thing as this equation. Square both sides of the Pythagorean theorem. X squared plus y squared equals a squared, or in other words, that's giving me all the points exactly a away from my origin. Same thing.
Yeah.
You with me on that?
Yeah.
So we just need to calculate the integral of the top half of this thing. And then double it.
Oh, we did do this.
We did do this.
Okay.
So I need to come up with a function for the top half of that thing. So I need to solve this thing for y, but only for the top half. So y squared is equal to a squared minus x squared. Or in other words, y is equal to plus or minus, but we're only going to do plus because we're talking about the top half. The square root of a squared minus x squared, top half of a circle. Now, if this is the origin, what's this coordinate point?
A.
A. And what's this one?
Negative A.
Negative a. So now we need to calculate the integral from negative a to a of this function, which is the square root of a squared minus x squared with respect to x, right? Ooh, did we do this?
I remember you do.
We gotta do trig substitution. Son of a gun. Nope, we haven't done this because we can't do this yet. Because I have to do trig substitution.
Oh, so you can't prove to us that.
So I can't prove to you. I thought I did. I lied to you.
We did it. We did an integral like that.
No, we don't have chapter 7 yet. Chapter 7, I think, is where you go over trig substitutions. Shoot. Sorry, that was a bad detour. Trig substitution is a super hard concept. I just don't want to go too far down a tangent.
We don't
Yeah.
do chapter 7.
I know. That's why I'm saying shoot. Because we never get to it. So, sorry, so far you just have to kind of take my word for it. Okay, area of a circle, pi r squared. And that's going to be the main formula that you need to know for area to start calculating a lot of the weird ones that we do, but first let's do a straightforward one. Okay, so first we're going to calculate the volume of a pyramid whose base is 3, and what's the height? And it's 3 meters high. Okay, so we've got some pyramid. Once again, I have terrible drawing skills, so I'm going to have to use your imagination a little bit here. We've got some pyramid. The base is 3 meters. The height is 3 meters. And it has a square base, so this is also 3 meters. You with me? Our job is to calculate the volume of that thing. Good?
Okay.
Okay. So, first thing I need to do is I need to redraw this picture inserted in some convenient way into an XYZ plane. That's always the first step.
Okay.
Try and come up with some convenient way to represent this. Well, actually, typically you'll be given functions that force you into viewing it one way in the XYZ plane, but
Isn't there a way to already calculate that area?
yes, we're going to start with really simple shapes and get to ones that you couldn't have calculated from grade school math.
Without integrals?
Yeah, there's formulas that you can use. Okay, so let's calculate this line. Now I'm going to redraw that thing in a very straightforward way now. So here's my pyramid. And I'm not even going to bother with the third dimension. I just plug it on the side with the square base like that, and then it comes out like this and comes to the tip. This is centered on it, so it goes both ways. So let me draw a bird's eye view looking down on this thing.
That would help.
Where's the X and Y?
So here's my X. Here's my Y. And then I just have this thing centered so its tip is right at the origin and it's going out like that. So it's going out of the whiteboard halfway and into the whiteboard halfway. You with me? So one of the base corners of it would be like right here, another one right here, those slanting in, and it has 2 more corners all the way through.
You mean like the base?
Yes, the base of the pyramid is right here.
Isn't the base a square?
I'm only drawing it 2-dimensionally to make so that we can integrate it easily. I'm taking this thing and I'm sticking it right here. Here's the tip. So some of it comes out, some of it goes in. You with me?
So along the x-axis is a line.
Along this x-axis is going right down its origin. Right down the center of it.
Okay.
Good?
I think so.
If I were to look at it down the x-axis, so if I'm looking down the x-axis,
Then it's a square.
so this is looking down the x-axis, we would just see the square like this, with the 4 corners coming together at the x-axis. And this part's further down. I'm a terrible artist, so you're going to have to deal with this. Use your imagination. But now I think you understand what we're saying, right?
Yeah.
Okay. So now notice, what's this coordinate point right here?
3.
3. So that right there is 3, because that's the height of the pyramid. This right here is 1.5, this right here is 1.5, for a total of 3. Okay. What is the cross-sectional area at some random point? What's the cross-sectional area at some random point x?
Why are you taking it from some random point? I still
We need to come up with a general formula to calculate the cross-sectional area anywhere on the scene.
So, but it doesn't matter where, right?
I need a formula that calculates it anywhere. That's what formulas do,
Yeah.
right? When I say come up with a formula, when we have equilateral triangle for the area of that triangle, you need to give me a formula so for any x you choose, it spits out the area.
I see.
So we need a formula so for any x you choose, we get the cross-sectional area at that x. What is it? What's the area of the base of that thing?
9.
9. What about if I only went 2 meters down? What would the area of the base be?
2 meters down.
Yeah, so here's the top of it.
Yeah.
If we look clear at the bottom, so we go down 3 meters, what was our area?
9.
9.
What if we only went down 2 meters?
Should be 4.
What's the cross-sectional area right here?
4.
4. How are you getting that?
2 times 2.
2 times 2. What if I only went down 1 meter?
1.
1. What if I went down 0 meters?
Nothing.
0. And if I go down 3 meters?
None.
3, or 9, yeah. And so our area formula, in terms of x, is just equal to x squared. With how I draw my picture. What's the area when we plug in 0?
0.
0. What's the area when I plug in 3? 9.
Okay.
That just gives you the area of the base.
Cross-sectional area.
Oh, that's right.
Anywhere. For any point along here, I can tell you the area at that point. You say I want to know what the area is going to be at 2.71 meters, I can tell you. It's going to be this. Notice that this is only valid from 0 to 3. If you ask me for the area at 5 meters down, this doesn't make sense.
How?
Because our pyramid doesn't go that far down.
So this one's easy and straightforward, but how do you deal with more complex ones like the one you had before?
Let's wrap our head around the easy one and see if we can figure out how to set the integral and go from there.
Okay.
The hard part, 100% of the time with these problems, is going to be going from the scenario represented to you to the integral that represents the situation. So see if you can come up with the integral that we would use to calculate this volume now. So what is my integral going to be? What are my bounds?
0 to 3.
So we're going to be going from 0 to 3.
Do you use the x-axis on these volume
Huh?
ones? Do you use x-axis boundaries on the volume ones?
I could have used x, I could have used y, I could have used z. It makes no difference. If I would have called this thing y, and I would have called this thing z, and said my x-axis is the one coming out like this, then all that changes is my area at some point y is equal to y squared.
Okay.
Doesn't change anything.
But you could have used like -1/2 to 1/2.
Yes, and I could have also flipped it so that my base was down here, and now my area formula, if I would have flipped the base, instead of it being y squared, because now this is a y, it would be 3 minus y squared.
Okay.
So, however you go from your physical situation to how you draw it on here, ultimately changes what the integral is going to look like that you calculate.
Okay.
It won't change your overall answer. The volume's the volume. So yeah, there's a bunch of different ways we could do this. Good?
Yeah.
I think so.
Okay. So, what's my integral going to be?
Y squared dy.
Yeah, I'm going to write it this way first. I'm going to take my cross-sectional area times a small width. A small area, a cross-sectional area times a small width gives me a small volume.
Yeah.
Add up all those small volumes as y varies from 0 to 3, and you get your total volume. And as you know, this is the integral from 0 to 3 of y squared dy, which is equal to y cubed over 3, evaluated from 0 to 9, 0 to 3, which is equal to 9, right?
Yeah.
So this has a volume of 9.
Okay.
1/3 the volume of the cube with the same dimensions.
Okay.
Good?
On the simple one, yeah.
Okay. I'm going to flip my picture now, and we're going to recalculate the same thing again, just to help give you a sense of how to calculate these things and come up with your formulas.
Okay.
So let's redraw it, and let's pretend that maybe you didn't think to draw it that way. You instead thought to draw it this way. Because this also seems like a fairly natural way to have drawn it, right?
Yeah.
Your pyramid pointing this way. So now notice, my area, we'll go back to calling this x now since we did one with y. Call that y. Notice that my area, when x is equal to 0, when x is equal to 0, my area is 9. When x is equal to 1, what do we expect my area to be?
4.
4. When x is equal to 2, what do I expect my area to be?
1.
When x is equal to 3, what do I expect my area to be?
0.
0. So now I need to come up with a formula that does this for x. And it turns out that this is 3 minus x squared.
Oh, I see.
You see that? That's the hard part. It's doing stuff like this that's the hard part of these problems. And so now I know, okay, so I need to calculate my integral from, we're still going from 0 to 3 of, here's my cross-sectional area, 3 minus x squared dx, right?
Yeah.
And now this is what we calculate to get our volume. So this is equal to, we'll expand this out really quick, the integral from 0 to 3 of 9 minus 6x plus x squared dx, did I do that right?
Yep.
Which is equal to 9x minus 3x squared plus x cubed over 3. Evaluate from 0 to 3. You can see why the other way was much nicer. But still, this is equal to 27 minus,
27.
oh, that's not 27, 81, sorry. 81 minus 27.
81.
What am I doing? Thank you.
What do you say?
27 minus 27 plus
Why is,
No.
9.
yeah.
27's go out, and you're left with 9, same as before.
Okay. Is there any other ways to draw that?
There's an infinite number of ways to draw it.
I see.
It's just one way makes it easier to come up with the area function than another.
Mm-hmm.
But yeah, infinite number of ways to draw it. There isn't the right way to draw it. You see that the previous way made our math slightly simpler than this way. So there's just more clever ways to draw it. And coming up with a clever way to draw it can often save you a lot of algebra. So let's do another one. Oh goodness. Now we're going to draw this thing. Okay. Let's get the dimensions on the cylinder. So we've got a cylinder with a height, or with a radius of 3, circular cylinder with a radius of 3, and we're going to intersect it with 2 planes. Okay. So first off, we've got our cylinder. It has a radius of 3. You with me?
Yeah. 3 what? Just 3?
Meters, whatever.
Okay.
We're going to cut this cylinder. It extends, it doesn't say how far it extends. We're going to cut this thing with 2 planes. One plane is going to be cutting it, which is like the XY axis. So cut it so now it has a bottom. So one of our cuts is already done for us. That's the cut right here. Cut by that plane.
Okay.
The other one is going to be a cut at 45 degrees from this thing, from the origin at the base where we cut. So 45 degrees, we're going to take another cut and cut 45 degrees, and we're going to get a wedge out of that thing.
Okay.
So let me draw it just from a side picture and then try and draw it back on this picture. So imagine I have a perspective now so that my cylinder looks exactly flat. Right?
Okay.
If I change my perspective enough, then it looks like that.
Mm-hmm.
If I'm looking at directly dead on. Okay, so that point is this point, right? I'm now going to come through and cut this thing at a 45-degree angle. So I'm going to cut this thing at a 45-degree angle, which is going to give me this wedge,
Yeah.
right? So now for just that wedge, if we look at that wedge from a bird's eye view, what does it look like? It's going to look like half a circle.
Half.
Why is
Yeah.
that?
Half a circle. I'm cutting that thing at 45 degrees, so I'm running a plane through this thing. I'm slicing up from that point, running a plane all the way through it at 45 degrees. So I'm cutting it all the way through like that.
This is bird's eye?
No,
Then what view is it?
this is bird's eye after the cut.
Oh, okay.
This is looking at the cylinder, right? Now imagine I keep shifting down and down and down so I can't see as much as the top, and I'm getting closer and closer to the bottom. There's going to come a point where it looks just like that, right?
Mm-hmm.
So this and this are almost drawing the exact same thing. Now if I take this and I just run a slice through it all the way like that, take a plane and cut all the way through it like that, trying to draw kind of it right here, draw like that, we're only going to be left with half the cylinder, right?
Mm-hmm.
So that removes everything on this half, plus it removes the top of most of this half. So from a bird's eye view of this wedge, it's going to look like half a circle. So that circle is slanting up. So when I take that wedge, if I pick it up and look at it like this, it's going to look like this.
I see it. Nope.
You with me? Okay. So that's what we need to calculate the volume of. You good?
The wedge?
Of the wedge. What's left of this wedge? What's the volume of that wedge? If I know that this distance right here is 3, right? Since this is a 45-degree cut, I also know that this is 3. And I know that the shape that makes this half a circle.
How's the height? You're right.
Because it's a 45-degree cut.
Yeah.
That's how we know. So, here's my XY plane. What's going to be the best way to draw this? Here's 3. Here's 3. So here it is in the XY plane. Maybe if I look at a picture of the authors, I'll be able to try and make this look three-dimensional. No chance. You know what? We could probably pull this off. We'll try it. I'll try and make this look three-dimensional. So we got, here's one axis, here's the other axis, X, Y, and then Z is going up. Here's my X, here's my Y, there's my Z. Okay, so here's 3, here's the wedge, and it's going to come up about like that. And then, there's just no chance. There's no way I'm going to draw this right. Okay, you can look in your book for an actual picture. I think I'm just going to make it worse. So, we'll have to stick with my very crude drawing. Here's the wedge. There's the wedge, and it wraps around,
Yeah.
and covers half a circle. Now we need the cross-sectional area of somewhere on this wedge, right? I need to be at some point x, if we call this our x-axis, I need to be able to figure out the cross-sectional area at x. So coming back and looking at this picture, remember, this is this tipped on its side, right? That means I need to be able to find a cross-sectional area at some x. Some x right there, and here's it looking at it from a bird's eye view.
Okay.
This is the plane I need to get a cross-sectional area of. If I cut out this piece right here, that's the same as cutting out this piece right here at x. Drawing this, here's my x coordinate system, going through it like that. Maybe should have done with dots. This is just getting atrocious. Can't draw. So, how do I get the area at some point there? I need to be able to do height times width, right?
Isn't it more complex than that?
No. Height times width always gives you cross-sectional area.
Oh, of cross-sectional area.
Right.
You first
So I
need
need
to know
this
the area.
distance right here, which is the distance across the wedge, and I need to multiply it by this distance right here, which is the height at that point on the wedge.
Yeah.
And that's how I get it.
Okay.
So I need that distance, and I need this distance. Well, what is this distance? So my area is some point x. That's the function we're looking to. What is this distance right here?
Yes.
X.
Just x, because this is a 45 degree.
Yeah.
So this distance and this distance are identical. So if I go over x, I also go up x.
Okay.
So the height for any wedge is just going to be x. You with me so far?
Yeah.
X times.
Now I need to calculate the distance across the wedge.
And it's just half a circle, so it's the area of half a circle, right?
No. Let me redraw half my wedge. So half my wedge. My drawing skills are just not with me today. Okay, so here's our origin, right? Here's the x-axis, here's the y-axis. So we're over here at the coordinate x, right? I need to be able to calculate the distance from here to here. Right?
Yeah.
If I can find the y-coordinate here, the y-coordinate here gives me this distance, and then double it gives me that whole distance.
Well, isn't the y just... Oh, no,
Yeah, we know how to get that. What's the equation for a circle?
pi r squared.
X squared plus y squared equals r squared. The equation of a circle.
Oh, the equation.
The equation of a circle, we know that the circle has radius what?
3.
So I know that x squared plus y squared is equal to 3.
Okay.
Yeah.
Or in other words, y is equal to the square root of, 3 squared. 9 minus x squared, if you solve for y. And only take the positive value because we're saying this distance right here. So that's this distance, so what's this whole distance? 2 times that.
2, yeah.
So our area, here's our height, times our width, gives me my cross-sectional area. So times 2 of those, so I'll say it's equal to, well, we'll leave it like this for a second, just so that we can see height times width. There's our cross-sectional area for anywhere on this wedge.
Okay.
Now notice, what do we expect the cross-sectional area to be at 0?
0.
0, because the wedge slants down and doesn't have any area at 0, right?
Yeah.
So plug in 0 to this thing, what do we get?
0.
0. And notice also, since the wedge rounds off, by the time we get clear to 3, how much area should we have at 3?
0.
0. And notice, when you plug 3 into this, what do you get? 0. If we're plugging 0, that means we have no height. If we plug in 3, that means we have no width. You with me?
Mm-hmm.
Just sanity checks to make sure we're not doing something crazy. Okay, there's the hard part, coming up with the cross-sectional area formula. Now that we got that, calculating the volume is easy. The volume is equal to the integral from
0 to 3.
0 to 3 of a of x dx.
That's dx. That's right.
The cross-sectional area times some tiny width gives me a small volume. Add up all those infinite volumes from 0 to 3, gives you the total volume.
Yeah.
Okay, which in this case is equal to, we have the integral from 0 to 3 of 2x square root of 9 minus x squared dx. I just put the 2 in front of the x. You with me?
Mm-hmm.
Okay, if now we do u substitution, u is equal to what?
9 minus x squared.
9 minus x squared, du is equal to what?
9 minus x squared dx.
Equals
Take the derivative.
2x, sorry. 2x dx.
Almost.
x3 over 2. No,
No.
you're right. It's
Negative 2x dx.
Yeah.
What's the derivative of 9?
0.
What's the derivative of negative x squared?
Negative 2x.
Okay.
Okay.
So now this is equal to the integral of, let's see, we have 2x dx, all we're missing is our negative. So throw negative in there. You with me?
Mm-hmm.
And we have square root of u du.
Yeah.
What are our bounds? When I plug 0 in for x, what's u?
9.
9. And when I plug in 3 for x, what's u?
0.
0. So notice we got a big number on bottom and a small number on top now. Uh-oh. So we got to flip it, right?
Yeah, which gets
No, we don't got to flip it. Oh, we could, and get rid of the negative if we wanted.
Yeah.
So, yeah. That's not a bad idea. Good thinking, actually. So, yeah, we'll do 0 to 9, get rid of the negative, and u, I'm going to rewrite that as u to the 1/2 du. Good? Which is now equal to, when we take the integral, what do we get?
2/3 u, 3/2.
2/3 u to the 3/2, evaluate from 0 to 9. When we plug in 9, what do we get?
3.
What is that? 9 squared, 27 times 2 divided by 3.
Divide by 3 first.
18.
Perfect. Square root of 9 is 3. So take the square root first. That leaves us 3. Cube it, we get 27 divided by 3 gives us 9 times 2 gives us 18. Good? Should we write it out?
That's good.
Good?
Okay.
So calculating the volume was real easy. The hard part always and forever, was calculating the cross-sectional area.
The area, yeah.
The cross-sectional area. The area at any random point along that figure. That's always going to be the hard part.
Okay.
Okay. So, now that we've done those two examples, finally, we'll get to ones that I can easily explain to you what's going on, and we don't have to rely on pictures anymore.
Don't you want us to draw pictures of?
Always with these problems, draw a picture. I'm saying that from what I draw to you, understanding the physical scenario will be real easy, whereas with these ones, you really need to do a picture to follow exactly what's happening. So our next one now is going to be, and these are more like the ones you're going to be typically solving. I want to take a square root function. Sorry, I just want to follow their exact example so that we can check an answer to make sure we didn't make a mistake. Y equals the square root of x from 0 to 4. Okay, so I'm looking at y equals square root of x. That's the function I'm plotting. So that's going to look something like at 1, it's going to be 1. And then by the time we get to 4, we're going to be 2. So it's a square root function. Something. Here's our square root function. And we're looking from 0 to 4. So we're cutting it off here. Cut it off there. You with me so far?
Yeah.
I'm taking this function. Here's my x-axis. Here's my y-axis. I'm taking that function, pivoting at this point, and I'm rotating it around the x-axis. And that's going to mark off a volume.
I see. So it's like a pyramid, except more rounded.
What do you mean rotating?
Imagine that this was an area. So color this in, this area. And forget my y-axis for a sec. Pretend I have this area as a piece of paper, and I'm holding it on a stick. You with me?
Yeah.
Now imagine I spin that stick. As I spin that stick, that thing rotates, right?
Yeah.
And it marks out a volume as it rotates.
Okay.
What's the volume it marks out? That's our question.
Okay.
So when we rotate that thing around, it's also going to come down here, like that, kind of, right? And as we rotate around, it's going to mark out the whole thing. So if we look at this thing from the base, what's it going to look like?
It's going to be
A circle.
a circle,
Right?
with radius 2.
So the point is a cross-sectional area, a circle with radius 2, perfect. But the shape is a circle.
Mhm.
So the shape of any cross-sectional area anywhere along this thing is just going to be a
Circle.
circle. And we know how to calculate the area of a circle.
Yeah.
The area of our circle is always equal to pi r squared.
Mhm.
So our area at some point x is equal to pi. What's our radius? What's the height from here to here?
It's f of y.
It's f of x, or y.
Oh.
Our y coordinate
Yeah.
gives us the height.
Yeah.
So y squared, pi y squared, or pi r squared for the picture that we've drawn.
Okay.
That gives me the cross-sectional area at any point.
Mhm.
And since circles are a lot easier, we could kind of get one of these. If I pick this point right here, the cross-sectional area we're talking about as a circle comes around like that, goes back around like that, and its radius is just the height of the function y.
Okay.
So what's our volume equal to?
The integral from 0 to 4 of a of x dx, which is pi y squared.
Pi y squared dx.
Root of x.
Squared.
Nope. Square.
Oh,
You see?
yeah.
So pretty simple calculation actually, right?
Pretty.
Oh, so you always want to convert back to x, or does it not matter?
No, we could have used y's. It's because of the way the picture drew. Look, if I'm integrating with respect to x, I can only have x variables in there.
Well, how do you know that you're integrating with respect to x?
Because of how I chose to draw my picture, I made so all my slices were along the x-axis.
Oh, I see.
I was calculating
I
the
see.
cross-sectional area at some x. If I would have drawn this so that it was facing up, then I'd be using y's. If I would have drawn so it was coming out, I'd be using z's.
Yeah.
And that just goes through and replaces all your variables in there with a different variable, but when you integrate it and plug in numbers, it's going to come out the same.
Mhm.
Right? So cross-sectional area, dx. Cross-sectional area gives me the area here. Dx gives me a small width. And so I actually calculated the volume of a small disk. Right?
Yeah.
So this is called the disk method. We're learning what's called the disk and then washer method for calculating volume. Why it's called disk method? Because we're splitting this thing up into a bunch, infinitely many little disks and adding up all those disks. When I take the area of a circle and multiply it by a little height, I get a little disk.
Yeah.
Add up all those disks to get our volume. That's what we're doing here, right? Okay, and so this is equal to, take our integral, what do we get?
Just pi x squared over 2.
Over 2, divided from 0 to 4, which is equal to,
Pi.
let's do the number first.
8 pi.
8 pi.
Yeah.
Right, 4 squared is 16, divided by 2 is 8. 8 pi.
Yeah.
Okay, so not so bad, right?
Yeah.
Well, let's do another one. Okay, let's calculate the volume of a sphere. Turns out it's easier to calculate the volume of a sphere when you know the area of a circle than it is to calculate the area of a circle.
How does that work?
So volume of a sphere, how could we do that? So I'm going to set my xy plane. I'm going to call this A. So we're going to do a sphere with radius A. You with me?
Mm-hmm.
And we'll try to draw a top half. So here's the top half of a sphere. If I take that line and I rotate it about the x-axis, that's going to trace out a sphere, right?
Mm-hmm.
So that's how we're going to do it. Almost identical to what we did last time.
Okay.
So for any, should we call this our x-axis and y? So I need to do it, if I'm going to add up a bunch of disks going along the x direction, I need to come up with a formula so that at any x, I can get my cross-sectional area at x.
Isn't it the same as last time though, except your bounds are just different?
It's the exact same as last time. Notice that all our cross-sectional areas are going to be circular. They're going to be disks
With the radius of y.
with the radius of
Or f of
the
x.
y. You're exactly right.
Okay.
So it's identical.
Yeah.
So our volume is going to be the integral from, here's negative a, right?
Mm-hmm.
From negative a to a of pi r squared dx.
Yep.
Good? Now we need to figure out what that y is in terms of x. I can't integrate y unless I have a dy in there.
That's right.
Yeah.
So what is my y?
Well, could you just...
What's the equation of a circle?
Y squared plus x squared equals a squared.
A squared.
Yeah.
It's a set of all points distance a from the origin.
Okay. So then y is just equal to the square root of a minus x.
Of a squared minus x squared.
Oh yeah.
Right? So that's my y. So plug that in here, and what do we get? Integral from negative a to a of, plugging that in, we have pi times a squared minus x squared. You with me?
Mm-hmm.
Because we squared it.
Yeah.
Now, probably should have used some knowledge that I had from last class. This function y squared is an even function
Because it's squared.
because it's squared. So going from negative a to a is the same as 2 times going from 0 to a, which will make plugging in slightly easier because we won't have to plug in negative a. So this is also equal to the integral from 0 to a, put the 2 out front. Let's pull out the 2 pi actually.
Yeah, that helps.
2 pi, the integral from 0 to a of a squared minus x squared dx, right?
Mm-hmm.
Okay, now let's integrate that thing. We're going to get 2 pi times, what's the integral of a squared?
A cubed over 3.
How do you do that?
A is just a constant.
So then it's a squared x.
A squared x.
Okay.
If we're talking about a sphere with radius 3, that's 3 squared. If we're talking about a sphere with radius 9, that's 9 squared.
That's right.
It's a stand-in for the radius. We're saying for any radius, here's how you get it.
If A is constant, can't you pull it out?
If I was to split this into two integrals,
Yeah, but we don't do that.
Oh, that's right.
so let's write out what you're saying just to make it very clear. I could have said this is 2 pi all times, and then we have a squared times the integral of dx minus the integral of x squared dx. And I could have written it this way and calculated those separately. And that's what we're doing in our heads when we calculate this.
Okay.
Okay? What's the integral of this?
That's negative x cubed over 3.
And we're evaluating this from 0 to a. When we plug in 0, we just get 0, so all we have to do is plug in the a. Right?
Yeah.
So this is going to be 2 pi times a cubed minus a cubed over 3. So if I have 1 a cubed and I minus a third a cubed, how many a cubes am I left with? 2/3 a cubed. Which is equal to 4/3 pi a cubed, or 4/3 pi r cubed, which is the formula you memorized and then forgot back when you were in 6th grade. That's the volume of a sphere.
Oh. Okay.
Pick a sphere of any radius, that gives you the volume.
Yeah, and instead of memorizing it, we actually know how to get that.
Yeah, it's not that hard of a calculation.
But you have to write it down.
And this is, in a sense, the way Archimedes figured it out. Kind of.
Really?
Yep. Just, he couldn't have written it this concisely because he didn't have the notation, he didn't have calculus. It's one of his most proud achievements, so it's one of the formulas that he had carved into his tombstone when he died.
I mean, if I figured that out, I'd be proud.
The other one was that, I might be lying, but I think the other one was that the surface area of a sphere is equal to 4 pi r squared, which means the surface area of a sphere is 4 times the area of a circle. How does that make any sense? And we'll calculate the surface area of a sphere.
That's pretty neat.
Okay, so we did a sphere, 4/3 pi r cubed. Next, find the volume of the solid generated by revolving the region bound by y equals the square root of x, the line's 1, and then x equal to 4, about the line y equal to 1. Okay. That's annoying. I guess to show you can rotate around anything. Okay, so the next one we're doing is we've got our square root function. No, we go that high. Square root of x, so when we go through 1, we go there, and when we go through 4, we go up to 2. Something like this. Sorry, that was awful. Good enough, though. Okay, so there's y equals the square root of x, right? We're supposed to find the volume of the solid generated by revolving the region bounded by y equals x squared. There's that region. The line y equals 1. The line y equals 1 is this line. Y equals 1. And the line x equals 4. X equals 4 is this line. So that leaves us with this region. Is the region they're talking about. You with me?
And it's asking for the volume if you revolve it.
The volume, if we revolve it, about the line y equals 1. So we're spinning this line right here and rotating it around that line.
Okay, so the area is the same. Well, the intersection of the area is the same.
Well, since this is shifted up, it's going to make our calculation a little bit weird. So when we're trying to figure out this radius, the radius is the distance from here to here. Right?
Yeah.
How do we find this distance?
Y minus 1.
Y minus 1. Perfect. You do the top point minus the bottom point.
Yeah.
Perfect. So our area function at some x is going to be y minus 1. That's our radius. squared times pi. Pi r squared. You with me?
Yep.
Now we know that y is equal to square root of x. Right?
Yeah.
So this is the same thing as square root of x. Let's do the pi first. Pi times the square root of x minus 1 squared.
Can we simplify that out further?
We can multiply it out if you want. So this is equal to pi times x minus 2 square roots of x plus 1. And then that's about as much as we can do with it. Okay, so our volume now. Tell me what to write. Volume is equal to what?
Integral from 1 to 4 of a of x, which is, yeah, dx.
Perfect. And so now we're basically ready to just calculate this integral, right?
Would it be easier to just make those parentheses just u?
No. Treat this as 3 separate integrals. They're already real simple. The integral of x, we know how to do that. The integral of negative 2 square roots of x, we know how to do that. The integral of 1, we know how to do that.
Okay.
Just integrate.
Okay.
Maybe, in case I'm losing you a little bit, pull the pi out of the whole thing. And instead of square root of x, I'll write x to the 1/2.
That helps.
Is that better?
Mhm.
Okay. So now this is equal to pi times, what's the integral of x?
X squared over 2,
Squared over 2.
then minus 4/3 x to the 3/2
Good.
plus x.
Evaluated from
1 to 4.
1 to 4. So we got to plug 4 into this and then subtract what we get when we plug 1 into this.
Yeah.
Right? So this is equal to pi times, let's see, when we plug in 4, what do we get? 4 squared over 2 is
8.
8. Let's see, square root of 4 is
2,
cube it
8,
times 4.
32.
And then we can't divide it by 3 evenly, so it's just 32 over 3, right? Plus 4. Let's really quick get this all in terms of thirds and see what it comes out to. So we have
4/3.
24 minus 32 plus 4 all over 3. Did I do that right?
No, you didn't convert your 4.
Oh, thank you, 12. So 4/3
Yep.
minus what we get when we plug in 1. So when we plug in 1, we get 1/2 minus 4/3 plus 1. So get it all in 6. So we're going to get 3 minus 8 plus 6 over 6, right?
Mm-hmm.
So what are we left with?
1/6.
1/6. So I got to do 4/3 minus 1/6. Or in other words, I got to do 8/6 minus 1/6 leaves me 7/6. All right, let's make sure we didn't make a mistake. 7 by 6. Okay, we did it right. So, in general, when we're using what we call the disk method, here's how you can always calculate it. It's going to be the integral from a to b of pi times our radius at x squared dx. That's our general formula.
Okay.
You just need to figure out what the radius is at some point x, and here's how you get it. Notice that this part right here is a of x dx. See, I don't like memorizing these types of formulas because I think you should just understand this and you're good to go. That volume is equal to a to b, a of x dx. That's all you really need to memorize. This is just a special case of that, when it just so happens that what we're using is circles.
What are we going to do volumes of trig functions?
I mean, it's possible that somehow this could be related to trig functions. That's very much the case. It's like take the first wave of the sine function and spin it around the x-axis and figure out the volume. You could easily get questions like that.
Well, how would you do that?
Same as you've been doing, all the problems you've always been doing.
I know, but
You're
how,
going to just have some function in terms of x with a trig function in there, integrated.
but how do you get that area? Is what I'm asking. I'm saying it's
Same
easy
way.
to do that.
So, okay, we'll do one.
Okay.
If you're this worried. We'll pick, let's see, which trig function is high at 0? Cosine? So we'll take the first section of cosine when it starts out at 1 and then it drops to 0. We'll take that first segment and rotate it around the x-axis. You with me?
Yeah.
So, drawing a picture, cosine starts up here at 1 and then it comes down to 0 over here at pi halves. I'm going to take that and rotate around the x-axis is what I think you're saying, right? So take this area and spin it around the
Is
x-axis.
that right? Cosine is 1.
Cosine is 1 and 0. What's your x-coordinate at 0?
X coordinate at 0 is 0.
At 0 degrees.
Oh, at 0 degrees. Okay.
There you go. Yeah, remember, trig function eats an angle. Anyways, so we're taking this and we're spinning this thing around, right?
Yeah.
So, our volume is going to equal the integral from, we're going to be going from 0 to pi halves, of pi r squared. What's my radius? What's the height from here to here? What's the height of this thing at some x?
Cosine of x.
Just cosine of x. So cosine squared of x, because it's pi r squared,
I'm still lost.
this distance from here to here.
Isn't sine the height and cosine this way?
Sine is the height on the unit circle. This is plotting your coordinate at a given angle. Maybe I should call this a theta axis. Okay, we'll call that the theta axis. Here's a theta, cosine of theta. What is your x coordinate when you plug in theta of 0?
1.
1. What is your x coordinate when you plug in theta of pi fourths?
Root 2 over 2.
So at pi fourths, it's going to be root 2 over 2, which is some number less than 1, but greater than a half. Over here at pi thirds, what's the x coordinate?
The x coordinate is 1/2.
1/2. Over here at pi halves, what's the x coordinate?
0.
So
Yeah,
we're
I see
plotting
what's
the
going
x
on.
coordinate for any
Okay.
angle.
Okay.
We're not plotting any unit circle.
Gotcha.
Okay.
So why is it cosine squared of theta then?
Okay. So now that I think you're back to wrapping your head around the picture.
Yeah.
Okay. So pick any random theta.
Okay.
Here's some random theta, because this is our theta axis.
Mhm.
I'm rotating this thing around the theta axis. So my cross-sectional area is going to be a disk. It's going to be a circle, or my cross-sectional area is going to be a circle.
Oh, so it's just r squared.
So pi r squared. My radius is going to be the distance from here to here,
Yeah. Which is cosine.
which is cosine theta.
Gotcha.
So pi r squared is my cross-sectional area, times the little widths I'm using. I'm using little d thetas.
And then yeah, we're good from there.
And yeah, we calculated that integral last class, without pi. Good?
Yeah.
Okay. Next example. Find the volume of the solid generated by revolving the region between the y-axis and the curve x equals 2 over y from 1 to y equals 4 about the y-axis.
So this one we're doing around the y, not the x-axis.
Yeah, so we're just going to get functions in terms of y, and we're going to have a dy.
dy. Gotcha.
So let me get my function again. It's x equals 2 over y. And we're doing this for y between 1 and 4. And we're rotating around the y-axis. Okay. So we are a picture. Now, remember always and forever, if for some reason treating x's and y's different confuses you, you can always treat this as your y-axis, this is your x-axis, and then it will come out exactly how you're used to doing it.
Can we do it that way?
Now, I want you to try and do it this way if you can, but if you're getting stuck, that's a fallback. But I want you to be able to just see it this way if you can, because ultimately you need to get to the point where you can just see it this way. We don't have time to redraw every picture to make it appeal to your intuition best. But early on, that is a very useful method for making these problems make sense. So let's plot this thing. So when y is 1, what's our x?
Our x is 2.
2. So if I have a y of 1, I have an x of 2. When y is 2, what do we get?
X is 1.
X is 1. When y is 3, what do we get?
2/3.
2/3, which is a little less than 1. And when y is 4, what do we get?
1/2.
1/2. And so this function on this interval, I mean, it comes like that, but we just care about right here. So try and draw it out for just a portion that we care about. So we're taking this area and rotating it around the y-axis, and it's the volume that maps out.
Okay, I see what it's doing.
Okay, so tell me the integral we're solving.
It's from 1 to 4
Perfect.
of, well, what's the area?
Still going to be a circle, because we're just rotating it, and it's metric.
So what is
So
it?
pi r squared.
So
Pi, what is this distance from here to here for a random y? If I pick a random y, what is the distance from here to here?
X.
It's just x. So pi,
Okay.
tell me,
X squared.
x squared
Dy.
dy. Now we have a dy, we have x's, so I need to rewrite x in terms of y, which, right there. So this is equal to the integral from 1 to 4. I'm going to pull the pi out. You with me?
Yeah.
And I'm also going to pull, we're going to get, when we square this, we're going to have a 4. So I'm going to do 4 pi times the integral from 1 to 4 of 1 over y squared dy. Did you follow that?
No.
Should have. By the time you can do that, I could have just done both of them. Should be so lazy. 1 over 4 pi times 2 squared over y squared dy, which is equal to 2 squared is 4 with the pi, is 4
Why
pi.
are you doing 2 squared and y squared?
Okay. 2 over y squared
Oh, okay.
dy is equal to, pull the pi out, 2 squared is 4, so
you
we'll
can
have
pull
4
the
pi.
out, yeah.
Okay, integral from 1 to 4 now, 1 over y squared dy. With me? And we'll rewrite it one more way to help you calculate the integral. Y to the minus 2 dy. Okay, now I think you can take it from there. What's that integral?
Well, 4y times
We'll do 4 pi first.
y to the negative 1 over negative 1.
So negative 1 over y, right?
But then why is it negative?
Good?
Mm-hmm.
Okay. And then, oh, that's the whole thing. Evaluated from 1 to 4.
Yeah.
Now I'm going to take this negative and I'm just going to pull all the way out there,
Okay.
so that we don't need to worry about it early on. So this is equal to negative 4 pi times, let's see, when I plug in 4, what do I get?
1/4.
1/4. Subtract
1.
1. So this is equal to negative 4 pi times what?
Negative 3/4.
Negative 3/4, which is equal to
3 pi.
3 pi.
Pi.
Notice, answer came out positive. Can't remember which of your guys' tests I was doing, but on one of your tests, you were calculating volume, I think, or area, and spitting out a negative number. Doesn't make sense.
And
Oh, it was when we were supposed to find the dimensions of the can, one of you gave me a negative radius as your answer, like negative 2.6 centimeters or something. Instantly, when you see something like that, it doesn't make sense. You can't have negative distances. You have negative displacement, can't have negative distance. Can't have negative areas. Can't have negative volumes. So if this did come out negative, then we knew we made a sign error somewhere, which is very probable.
Yep.
You'll make a lot of sign errors. So make sure it makes sense. 3 pi, got the same thing. Okay, now what are we doing? Find the volume of the solid generated by revolving the region bound by the parabola x equals y squared plus 1. And the line x equals 3, about the line x equals 3. Okay. And I don't need all that. I'll erase it later. So we had, just new problem, we have x is equal to y squared plus 1. They're giving us it in terms of x, so that's probably how we're going to work with it.
Okay.
And x is equal to 3. So the region bound by these two functions rotated around the line x equals 3. Now so far, hard for you to see exactly what that's saying. Draw the picture, and then it'll become obvious what this is saying.
Did you give any boundaries?
Huh?
Did you give any boundaries?
No, we don't need them. So, when x is 0, oh, doesn't make sense when x is 0. Sorry. When x is 1, what's y?
Don't you want to say if y is 1, what's x?
Okay, if we plug in 0 for y, what's x? 1. No. Yes.
Yes.
Sorry. If we plug in 1 for y, what's x?
2.
2.
If we plug in negative 1 for y, what's x?
2.
2. Right? If we plug in square root of 2 for square root of 2 for y, then x is 3. So by the time we get to x equals 3, first let's just draw a line x equals 3. That would have probably been helpful to draw first. There's x equals 3. By the time we get over here, we're up to square root of 2 and negative root 2. Right?
Yeah.
So this is root 2. This is negative root 2. And so it's this sideways parabola. And we're supposed to rotate that around the line x equals 3. So we're talking about this region, about this line.
Okay.
Okay. So, cross-sectional area. So when we rotate it, it's going to come back down on the other side. So it's going to come back like this, right? When we rotate it. So we're saying the volume of this whole thing is what we're looking for. But what's the radius? What's the radius of one of the circles? So we have some circle, some arbitrary circle. So for this arbitrary cross-sectional circle, what is its radius? R.
Y minus R.
So we're looking for the area at some y. It's equal to what?
It's going to be Y minus something, right?
No. I'm looking for the distance between this point and this point.
That's 1.
This is completely in the x-axis.
Oh.
What's this point?
3.
3. What's this point?
2.
The x-coordinate of my function. In this case, it's 2, but I'm saying for a random point.
Oh, so it's just 3.
It's just 2 minus the x-coordinate of my function. Squared.
2. Why is it 2?
Times pi.
2.
No,
3.
3, sorry.
There you
I don't know where 2 came from. 3.
That's a perfect circle.
That's the radius.
go. Okay.
No, that is not a perfect circle.
I mean,
The cross-sectional area is a perfect circle. Because I'm taking this thing and I'm rotating it around this axis, which traces out a perfect circle. A bunch of perfect circles, right? So the cross-sectional area is a perfect circle. Does that make sense? Okay. So that's our radius. That's the hard part. So what's the volume? Volume is equal to the integral from where to where?
From 1 to 3, or,
Yeah.
From 1 to 3.
right?
Mm-hmm.
Or do you want to go all the way around?
No, it's not from 1 to 3.
So 1 to
Which direction am I taking small slices? In my x direction or my y direction?
y.
My y direction.
Yeah.
So my dy's, so I'm using dy's, not dx's.
Oh, then it's
So root
negative
2
root 2.
is
There we go. Negative root 2 to root 2.
Okay.
Okay. A of y dy,
Yeah.
which is equal to the integral from negative root 2 to 2 of
root
2, thank you, of pi r squared. Maybe we'll simplify this thing out really quick before we substitute it in. First off, we know we want y's, not x's, right?
2.
Mm.
So I need to rewrite x in terms of y.
Root of plus 1. Oh, that's right.
Minus, because we're being subtracted. Negative x is the same thing as negative y squared minus 1. Okay? So this is equal to, simplify that really quick, we get 2 minus y squared times pi. Right?
Oh,
Just
yeah.
combine the 3 and the negative 1.
Yeah.
Okay. Now we can multiply that out. I'm going to put my pi in front. Pi times 4 minus 4y squared plus y to the 4. So this is equal to the integral of, maybe I can pull the pi out. You okay with me pulling the pi out as I go to make the substitution?
Yeah.
Because I'm substituting in a of y, which is that whole thing. So the integral from negative root 2 to root 2 of 4 minus 4y squared plus y to the 4 dy, which is equal to, notice, it's a polynomial. All the terms are to even exponents. This is 4 times y to the 0, 4 times y to the 2, this is y to the 4. It's an even function. Therefore, I can rewrite this as 2 pi, the integral from 0 to root 2, just to make plugging in a bit easier, of this thing. Oh. Oh no, that was right. Y to the 4 dy. Okay, now we calculate our integral. So it's going to be 2 pi times
4y minus 4y to the 3 over 3 plus y to the 5 over 5.
which is equal to, evaluated from 0 to root 2. Right? Which is equal to, we still have our 2 pi, times, we're going to have 4 root 2, minus, root 2 cubed is going to be 2 square roots of 2 times 4, is going to be 8 square roots of 2 over 3. With me on that?
Yeah.
And then plus, this one,
16 root 2.
not quite,
8.
Oh, it's just 4.
4 square roots of 2. Square root of 2 times the square root of 2 gives me 2. So 2 square roots of 2 gives me 1 2. So 4 square roots of 2 gives me 2 2's,
Yeah.
with a remainder of 1 square root of 2. Okay. So now this is equal to 2 pi, common denominator is going to be 15, right?
Yep. Yeah.
So 4 times 15 is 60. So 60 root 2 minus 40 root 2, multiplying the 8 by 5, plus 12 root 2. multiplying the 4 by 3, all over 15. You with me?
Yep.
Okay, so 60 minus 40 leaves me 20, plus 12 gives me 32, times 2 gives me 64. 64 pi root 2, all over 15. Or maybe 64 root 2 pi. It's probably the better way to write it. Probably I got 15. Something like that.
Okay.
Oh, they did it how I got it before. 64 pi root 2 over 15. So we got the same thing. So we did it right. Okay. Our next example, we upgrade from just the disk method to the disk and washer method.
Just a washer.
Yeah. What's a washer? We're talking about a washer as in a washer that you use in construction.
It's missing a
So
lot.
it's a disk, but it's missing a middle part.
Mm-hmm.
So the same way that we figured out how to calculate the area between two curves, you did the top curve minus the bottom curve, we're now going to calculate a volume between two curves. It's going to be the outer volume minus the inner volume.
Okay.
So, pretty straightforward. Let's see an example and then we'll write the formula. But again, I hate the formula. I think the only formula you should memorize is the integral of ax dx gives you your volume. And you should be able to just think about these things and come up with formulas yourself as you need them. But the book gives you the formula. They spend a lot more time in education than me, so maybe you should listen to the book and not me. So, let's see the example. The region bounded by the curve y equals x squared plus 1. And the line y equals, was it negative x plus 1? Negative x plus 3. And we're revolving about the x-axis. Okay. So, oops. They didn't give us any bounds, so we're going to also have a negative direction. Sorry. Maybe a little bit better. But we only care about positive. Okay. Okay, so y equals x squared plus 1. That's parabola pointing up, goes through 1. Over here, goes through this point, over here. Goes through this point, and this point. There's our parabola.
No, that's too much.
What? Is it?
It's 2 to 4, not 2
You're
to
at
5.
That's because the whole thing shifted up one. 2 squared plus 1 is 5.
Oh, I see.
Okay, so terrible, terrible, terrible. It's because my axis is all sorts of garbage. Need like a graphing whiteboard. Okay, terrible, but you understand the picture. This line, 1, 2, 3, with the slope of negative 1. Right?
Mm-hmm.
So, okay. The region we're talking about is this region.
And that's rotated about the
And we're
x-axis.
rotating it about the x-axis. So we're taking that and we're rotating it this way. So it's going to come, mark out a volume, and then go down there. So it's going to be a really weird shape with part of it hollowed out.
Yeah.
Rotating on which x-axis?
The x-axis, this one.
Starting at.
So it's right here. It's going to rotate out of the whiteboard and go back in down here. Go around and come back out. So a really weird shaped donut looking thing.
Yeah.
You with me? Now, we don't know how to do that. If you ask me to just rotate the region down here, if you ask me to just rotate the region underneath this curve around the x-axis, we know how to do that. And if you ask me to rotate the area under this curve around the x-axis, we know how to do that. So for both of them, we just take the difference.
Oh, I see what you did.
So your first one.
So you need to find two areas.
So first, I'm going to take this line, negative x plus 3, and rotate that around the x-axis. And that's going to give me a solid volume all the way through, right? And then I'm going to find the volume if I rotate the bottom up under this parabola, this area, underneath the curve. And I'm going to rip that part out. I'm going to remove that volume, which leaves me with this part of the volume. Does that make sense?
Yep.
Yeah.
So I'm going to call, here's the formula that they give you. The volume is going to be the integral from a to b. In our case, it's going to be, well, we'll just write the formula. A to b of the outer one, our outer area is going to be pi times big R at x squared. To remind you, that's our big circle. Minus pi r of little x squared. Subtracting out the inner circles, and that leaves me now with just a washer.
They're both circles?
They're both circles.
But isn't...
Let me do a really simple case for a second, one that we can draw easily and just say we're rotating it. Let's say I'm rotating that line about the x-axis, which just gives me a cone.
A cone.
A cone. If I take this line, let's go from here to here, this area, and I rotate that around the x-axis, that gives me a cone.
Oh, I
like
see.
an ice cream cone.
I see. Yeah.
You see that?
Mm-hmm.
Now, imagine that I did something like this, and I said, I want a cone, but I want part of it hollowed out. So I want to subtract away this part. So now I just want to take that area and rotate around the x-axis. The outer part still looks like a cone, but the inner part has some of it missing.
Yeah.
Right? How do I do that? What are the cross-sectional areas of this thing look like? So when we rotate it around, we have our bottom one here, and then one like that, right? If we rotate all the way around.
Mm-hmm.
And so we're talking about this. What does a cross-sectional area look like?
It's...
Let's call this distance from here to here. We'll call this distance little r. And we'll call the distance all the way out to here big R. You with me?
Mm-hmm.
So cross-sectional area of one of these things, so cut this thing out, cut a piece out right here. So it has a width here of dx. So that's my dx, right? And I'm cutting that out of the whole thing. So I've got a bottom one and a top one. And now I'm going to look at it from looking this way. It's going to look like a washer. It's going to look like a washer where the distance from here to here is big R, but the distance from here to here is little r. And we're talking about this is our cross-sectional area.
I see.
You see that?
Yeah.
That's the same idea, regardless of how crazy the shape gets. So my cross-sectional area, maybe erase what I was doing here before, and then we'll just plug in when we're done. My area of this thing, area is equal to the area of the big circle minus the area of the little circle.
Yeah.
The area of the big circle is pi big R squared minus pi little r squared.
Okay.
Or in other words, it's equal to pi times big R squared minus little r squared.
Mm-hmm.
Now, if my area is changing with x, then our area function is going to somehow depend on x. And our radius is somehow going to depend on x, right?
Yeah.
So, if we're a little bit more general now, I'm going to say the area at some point x is going to be pi times the big radius at x squared minus the little radius at x squared.
Okay.
Take our integral, so we're going to be doing the integral on some bounds of a to b of pi big R of x squared minus little r of x squared dx gives us our volume.
But your big R and your little r are just those functions, right?
No, not necessarily. Typically, but not necessarily. We can come from cases where it's not that.
Okay.
Our first case, it's probably going to be that. So yeah, now you're realizing, okay, this distance right here, little r, that's just the y-coordinate of this function, And big R, that's just y coordinate of this function.
Yeah.
And in that case, and so in this special case, yes, that is the case. So the volume now is equal to the integral from, remember, we're doing small little x's, so we're counting our x's. Our left-hand x is -2, and our right-hand x is 1. So this point right here is -2, this point right here is 1. That's where these two things intersect. With me so far?
Yep.
So -2 to 1 of our cross-sectional area, is going to be pi times our outer radius squared. Maybe I'll do square brackets here. Our outer radius squared. What's our outer radius? -x plus 3.
Yeah.
Squared minus our inner radius squared. What's our inner radius?
X squared plus 1.
Squared dx. That's the integral that we're solving.
Okay.
And then from here it's just math. Setting it up is always the hard part. So this is equal to, first off, let's pull out the, I say let's pull out the pi as I write my integral sign and don't pull it out. So pi times the integral from -2 to 1 of, let's square this thing out. We're going to get
X squared.
x squared minus 6x plus 9 for this thing, right?
Mm-hmm.
Minus whatever we get when we square this thing out. So maybe I'll do square brackets here, and I'll distribute the negative when we're done. So minus, when we multiply this thing out, we get x to the 4 plus 2x squared plus 1, all dx.
Okay.
Good?
Yeah.
So this is equal to, once again, pull out the pi. We have the integral from -2 to 1 of, let's see, we have an x squared minus 2x squared. Well, let's do our x4 term first. So how many x4s do we have?
Just 1.
-x4. Okay, we don't have any x cubes. How many x squareds do we have?
-1.
-1. And then how many x's do we have?
-6.
And then how many constants do we have?
8.
Right?
Yeah.
Okay. And maybe I'll just factor out the negative of that to make it slightly easier to integrate. So this is equal to -pi times the integral from -2 to 1 of x to the 4 plus x squared plus 6x minus 8 dx.
Okay.
So this is equal to -pi times
X to the 5 over 5
x to the 5 over 5
plus x cubed over 3
plus x cubed over 3
plus 3x
plus
x
3x
squared.
Why is that x squared?
3x
3x
squared
minus 8x.
minus 8x. And now we need to evaluate this from -2 to 1
Why is that x4 over 5?
because I wrote it wrong.
Okay.
Good catch. Okay, so this is equal to -pi times, let's see, when we plug in 1, what do we get?
1/5.
We have 1/5 plus 1/3 plus 3 minus 8.
Yeah.
So let's get it in terms of 15ths. So we have 3 plus 5, 3 minus 8 is going to be
Minus 5.
minus 5 times 15 is minus 60. No,
Minus
75. All over 15, right?
Mhm.
We do that right?
Mm-hmm.
3/15, 5/15, 15/15 minus 95/15. Not 95. What am I thinking? 90. Which leaves minus 75. Okay. Just thinking about it 2 ways to make sure we didn't make a mistake. Okay, so all in all, how many 15ths are we left with?
67. Negative 67.
-67 15ths. now we're going to subtract what we get when we plug in -2. All right, where's my chair? This is killing me. Okay, when we plug in -2, what do we get?
-32 fifths.
-32 fifths
Plus.
No,
minus
-8 thirds.
-8 thirds
Plus 12.
plus 12
Plus 16.
plus 16, right?
Yeah.
So let's get all over 15, see what we got. 32 times 3 is
96.
96, minus 8 times 5 is
40.
40, plus 12 plus 16 is
28.
28 times 15.
Pretty large.
28 is a multiple of 4, right? How many times does 4 go into 28?
7.
7 times. So, group 15 into 4s is 60, and we just need to do 60 times 7.
Which is 420.
You see how I did that?
Yeah.
That's often the way that you do arithmetic like this in your head. So we were just really trying to figure out 28 times 15. 28 times 15. That's too hard for me to think about. But I can think about 7 times 4 times 15, regroup these together as 60, and rethink about it as 7 times 60.
Oh, yeah.
And that's what I was trying to walk you through. I probably should have just written it. Anyways. All over 15 though, right? All over 15, and now we need to calculate this really quick. So when we do 420, let's subtract the 96 first. Well, it doesn't matter when we subtract first. Maybe do the 420 minus 40, what does that leave me with?
380.
So I have 380, and now I'm going to subtract 96 from that. Or in other words, I'm going to subtract 16 from 300. It's easier for you to think about it that way.
384.
284.
Yep.
So 284 over 15. So, but that was positive, right?
Yeah.
284 over 15. Okay, so now we got to do 284 plus 67, and what do we get?
34 plus 67 is 351.
351. So we're going to have 351 pi over 15.
Okay.
Now that one got a little bit messy, so let's see if that's even close to what the author has. 117 over 5. So let's see, 117 times 3, what do we get? 351. Okay, same thing.
Okay.
Yeah, not so easy to see that since 117 is prime. Okay. Our next one. Some more Dishwasher Method. The region bound by the parabola y equals x squared and the line y equals 2x. Okay, that one's a lot more straightforward. And I assume it's about the y-axis. Revolve about the y-axis. Okay. That's some new high school game.
I have no idea.
Well, I knew who it was.
Who was it?
His name's Tyson.
Who's Tyson?
He's a sophomore.
What's his last name?
Zitty.
Lawrence.
He's Lawrence, Sophie's.
Okay.
Sounds like him.
Okay, so we're looking at y equals x squared and y equals 2x. And we're looking at the region revolved about the y-axis, is what we're going to rotate around.
Okay.
So, y squared, hopefully we can draw this okay. It's going to be coming out and going up like that, roughly. And then y equals 2x, that's nice and simple. That's going to be just that line. So we're talking about this area right here, rotated about the y-axis.
So kind of like a cone.
So kind of like a cone. Kind of like a cone, okay. Yeah, the inner volume that we're cutting away is a cone.
It's a cone.
And then
Okay.
the outer volume is some weird remaining shape. Okay, so we're going to rotate that around. Obviously, we're going to be using the washer method. So our integral, well, let's just start writing it out. You tell me what to write, actually. Where are we starting? Which way are we taking our slices? Are we taking our slices in the x direction or the y direction?
Y.
The y direction. We're taking our slices in the y direction because we're rotating this way. So our little widths are going to be delta y's, or dy, dy, dy.
Oh, so it's rotating this way.
It's rotating about the y-axis.
Oh, the y-axis.
So our washer is oriented this way, so our washers look like this. They're oriented this way,
Yeah.
but then they have a teeny bit of thickness to them, and that's how we're getting a volume. This volume is going to be dy, or that height is dy. Right?
Okay.
So we're taking our slices in the y direction, so we're going to be integrating in the y direction. So,
from 0 to 4.
perfect. Times pi, our outer radius is going to be,
Our outer radius is just x squared squared.
X4, because it's just radius squared.
we're looking for this distance right here. What is this distance?
That distance?
It's just X. No.
It's just x.
Yeah.
But then we have x on the other one. I'm now thinking weird.
It's since it's rotating around the y, don't you have to do it in y?
Because we are taking.
Yeah, we'll get it in y, but I need to resolve these for x's. So x is equal to the square root of y for this top one. And then here we have x is equal to y halves. Because we need to get our radius.
Yeah.
We need to get, so our distance to the outer one, the distance from here to here is our x, not our y. Y gives us the distance from here to here.
So our big one is just x squared.
So our big one is this. We have two different x's, so be careful which one, what you're saying.
Well, the first
If we
one
get it
is
in terms of y, what is it? Our outer radius.
X squared.
Square root of y
Square
is
root
our
of
outer
y.
radius. But you're going to square it, so you're left with y. So our outer radius squared is just y.
Oh, I see what you did.
That's this radius. This distance is square root of y. Square it gives us just y.
Okay.
Minus.
This radius, so we get minus, what's that radius?
Just y over
Y squared over 4.
Y squared over 4, yeah.
Right, the radius is y over 2, so when you square it, it's y squared over 4.
Oh, gotcha.
But yeah, you're thinking right.
Okay.
dy, that's going to be our volume.
Yeah.
Good? So there's the hard part, the rest of this becomes easy. Plot pi, we have integral 0 to 4 of y minus y squared over 4 dy.
You can pull out your 1/4, right?
You can, but then you have to multiply 4 into that.
Oh.
You have to get a common denominator before you factor, or a common numerator before you factor. You can factor out one term. Okay. Anyways, so now we can solve this integral. So this is equal to pi times, what's the integral of y?
Y squared over 2.
minus, what's the integral of y cubed over, or y squared over 4?
Y cubed over 12.
Perfect. And we're plugging in from 0 to 4. So this is equal to pi times 4 squared over 2.
8.
8. 4 cubed
64.
over 3 times 4. So we can think about this as 4 squared over 3, or 16/3. Follow that?
Yeah.
We have 4 cubed over 4 times 3, which is the same thing as 4 squared over 3, 16/3. Okay. So 24 minus 16, 8/3, 8 pi thirds. If you get a common denominator, multiply 8 top and bottom by 3, you get 24 over 3. 24 over 3 minus 16 over 3 leaves 8 over 3. Bring the pi back in.
Okay. That one was a lot easier than the last one.
8/3 pi. So we did it. Okay. Another method for calculating volumes is called cylindrical shells. Cylindrical shells. So when I have some random volume, I could break it up. How can I give an intuition for this? Maybe let's jump into an example and then try and generalize it as we do the example.
Okay.
So we're looking at the example, y is equal to 3x minus x squared. And the idea here is basically going to be that I don't just have to use a bunch of disks to break up a volume. I don't just have to approximate a volume using a bunch of disks. There's other ways that we can approximate a volume. And it's going to be using cylindrical shells. It's going to be the notion of how can I say this best? You know pipe fittings that barely fit into each other, right? So imagine I have a pipe fitting, and then inside that I put another pipe fitting that barely fits, and inside that I put another pipe fitting that barely fits, and keep doing that all the way down until I put it in just like a stick, right?
Oh, so you start out with like a solid line, and then you just add on to that kind of.
So we'll get into an actual example to get a feel for this.
Okay.
So let's see, the line that we were saying is y equals 3x minus 2. Minus x squared, not minus 2. I can say that minus 2. Minus x squared, and we're going to rotate around the line x equals -1. I don't know why they're making this messy for our first example, but let's stick with it. So let's draw the C real quick and then see how we're going to calculate the volume. So if we graph this thing, we won't need it down. I think it says and above the x-axis. The region enclosed by the x-axis, this upside down parabola. Okay, so the x-axis, we're going to have an upside down parabola and we're going to rotate around the line, x equals -1. So here's the line we're rotating around. X equals -1. And it's going to be an upside down parabola over here. Let's figure this out. When I plug in 1 for x, what do we get?
2.
Sorry, I don't know why I start with that. Start with 0. When I plug in 0, what do we get? 0. When I plug in 1 for it, what do I get? 2. When I plug in 2 to it, what do I get?
2.
-2.
Plug in 2.
Oh, wait.
Yeah, it's just 6.
It's still just 2, right?
Yeah.
And then when I plug in 4 to it, what do I get? Or 3, I mean. 1, 2, 3. 1, 3.
Yeah, you get 3.
No.
0.
0. You get 3 squared minus 3
Oh,
squared.
yeah, duh.
So this thing is going to have a max at 1.5, whatever it is.
1.5.
Mm-hmm.
Oh.
So the parabola is going to look something like this. You with me?
Mm-hmm.
Now we're rotating this around this axis, right? So it's going to come over here and we're going to have a similar shape when we rotate it around.
So it's like you have half of a sphere with a donut.
It's a donut. It's gonna, if you look at it from a bird's eye view, there's gonna be the missing hole and then the outer part, and it comes around the outer part.
Yeah, but it's a donut split in half.
Oh, the top half of a donut.
Yeah.
If you cut the donut that way, yes, I see what you're saying. Yeah, that's not a bad way to read it. Okay, now we know one way to calculate this volume already. We can calculate the volume using the Dishwasher method, right? I can do the outer volume minus the inner volume, and that will give me it.
Okay.
I can view a cross-sectional area as just a washer. And that's a perfectly valid way to do it when that works out.
Okay.
The second way to do it is I'm going to look at a single cylindrical shell of this thing, which means for some x here, I am going to calculate the volume of a small cylinder shell. So a small cylinder shell is going to start here. It's going to be taking this little piece right here and rotating that little piece around. So from a bird's eye view, here's my donut. I'm taking out a cylindrical shell, which is here, and goes all the way around like that. And I'm cutting that little snippet out.
I see what you're doing now.
So it's like I've got that donut, and I got a pipe fitting, and I shove the pipe fitting through so it like just cuts out that little piece equal to the pipe fitting.
Yeah.
Does that kind of make sense? So what is the volume of one of these little cylindrical shells that goes all the way around? So it's that little piece that wraps around, and it comes back over here, right here. What is the volume of that cylinder?
It's just the volume from the negative y all the way out.
So
minus
the volume of a single cylinder at x is going to be equal to, what's the volume of a cylinder? First off, it's going to be its height. Its height is just y, right?
Y
Yeah.
times delta x.
Y times, it's going to be the surface area of a cylinder times dx.
What?
If I had you, okay, so I take this cylindrical shell, right? So it's a circle inside of my donut. I'm going to take out that cylindrical shell and lay it out flat. You with me?
Mm-hmm.
So now I'm going to lay that shell out flat right here. And now we're looking at laid out flat. Good?
Okay.
Its width is going to be little delta x, or dx. So it has a little bit of width. Which is dx, right? What's the area, though? So the volume is going to be the area times dx, but what's the area of that thing? I need height times this whole distance. What's the height of this?
Y.
That's just going to be the y. That's the same thing as the height right here, right?
Yeah.
What's the width now? If we're looking at it for a bird's eye view, the width is starting here and going all the way back around to that point.
So it would be the circumference. of that.
Circumference of the circle.
Of a circle.
So it's going to be 2 pi times r, our radius. What's our radius in this case?
X.
Almost. Remember, we're rotating around x minus 1. So what's our radius?
X plus 1.
X plus 1.
Okay.
Okay? So I'm going to write down two different ways that we could have calculated this integral. Well, that's rough. No, I'm not going to do that. So that is one of these cylindrical shells. We're adding up all these cylindrical shells to get the volume, right?
I see.
So our integral, we're going to be adding up all these cylindrical shells. We know how to get a cylindrical shell for every x. Our x varies from 0 to 3.
Yeah.
So our x varies from 0 to 3. And we're going to be calculating the area of one of these cylindrical shells. So that's pi times y times,
2 pi.
let's do 2 pi times r. In general, it's r of x, some function r of x, times y times dx. That's in general what it is. 2 pi r times the height times dx.
Okay.
Circumference times height times dx, and add them all up for every dx. So that's what is in general. In our special case now, we're looking at the integral from 0 to 3 of 2 pi. Our r of x is x plus 1, right?
Yeah.
And our y is
3x minus y squared.
dx.
Oh, but you have multiplication now. Do you just multiply?
We always had a multiplication. We have circumference times height times a little dx. It's going to give me a little volume. I'm adding up infinitely many of those volumes as x varies from 0 to 3.
I get that, but how do you integrate for a multiplication?
You just multiply. Or you can do a u substitution if you see it that way.
I thought you couldn't do that. I thought you said something weird happens, and you can't multiply two terms in an integral.
I'm saying we don't have a product rule for integrals like we have for derivatives.
You want to just show me that?
Well, when we did something like the integral of sine squared, you had to go find some clever trig substitution to make that work. And okay, you know how to make it work for sine squared, but now what about if I make you figure out sine cubed d theta? You still don't know how to do this. But if I said calculate the derivative of that, you know how to do it. You just use the product rule. The product rule works for every single product out there.
Product rule.
For derivatives. You can calculate the derivative of that really easy.
Yeah.
But the integral is a pain. So for our derivatives, we have special formulas that we can always use no matter what. For any product, when you're calculating the derivative, you can use a product rule. For any quotient, when you're calculating the derivative, you can use a quotient rule. When you're trying to calculate the integral of a product, there's no rule that you can just use. You have to think about it and come up with a way to do it. That's what I'm saying. So I'm just telling you integrals are hard. You can always distribute that out. Algebra is still algebra. Algebra always works. You can always distribute. Doesn't matter the field.
What if you can't distribute them?
You can always distribute. When you have a product like this, you can always get rid of your sums and your minuses and put it all together.
Okay.
I mean, it's one of the axioms of arithmetic. Is your distribution law. So distributing is always legal.
That's an axiom?
Yes.
So we don't prove that?
You don't prove that you can distribute. It's an axiom.
Okay.
It's one of the field axioms. Anyways, so you can always distribute worst case. Sometimes distributing becomes a nightmare, right? If this was like to the 7, then maybe I tried to come up with some u substitution of this thing. So I didn't have to multiply that out.
Oh, I see.
I could still multiply it out. That's always valid. Sometimes you're creating a headache for yourself. So don't multiply out if you see a clever way to avoid it. But in this case, multiplication is so simple, it'd be just as hard to come up with a clever way to avoid it as to just do it.
Okay.
So 2 pi times the integral from 0 to 3 of, when we multiply this out, we're going to get 3x squared minus x cubed plus 3x minus x squared. Right?
Yeah.
Distribute the x through first, and then distribute the 1 through. And pull the 2 pi out front.
Isn't that negative x? Oh, you do have negative x cubed. Okay, we're good.
Okay, so this is equal to 2 pi. We're just going to combine like terms. First we'll write our x cubed term, so we have minus x cubed. Then we have plus 2x squared. Then we have plus 3x. Right?
Yep.
Now we can calculate our integral. This is 2 pi times the integral. So negative x to the 4 over 4 plus 2x to the 3 over 3 plus 3x squared over 2. Evaluated from 0 to 3. We just need to worry about plugging in the 3 term. So this is equal to 2 pi times, when we plug in 3, we're going to get negative 81
Yeah.
over 4 plus 54,
Mhm.
is that right? Over 3 plus 27 over 2. Good? Or did I make a mistake?
No, we're good.
Okay, so this is equal to now, we still have 2 pi times 12 is going to be our common denominator, right?
Mm-hmm.
So we have negative 81 times 3. Sorry, that's a 243. Negative 243 plus, we need 54 times 4. And then plus, now we need 27 times 6. All over 12.
Which is 216 on 12.
No, I messed something up. That was not right. I thought I saw a trick that wasn't a trick. 27 times 6 is the same thing as 81 times 2, which is 162. Right? Did I do all those correct?
Yeah. Yeah.
Okay, so I'll pull my 12 out here with my pi. So we have pi over 6 times, and figure out what these all add up to. So 243 minus 216, what does that leave me with? Is that 27?
It's 37, yeah, 27.
So negative 27, and then we're adding 62 to that. So what does that leave us with?
135.
135. So that's equal to 135 pi over 6. Let's see. 135. Does 3 go into that?
Yes, it does.
Oops. 45 times 3. Oh, duh. 135, 135 degrees. On our unit circle, 45, 90, 135. That should have jumped out at us sooner.
So 45 over 2. 45 pi over 2.
So 45 pi over 2, correct. And so, there's the answer using cylindrical shells. So maybe write a formula now, really quick, for what we've talked about so far. So when we're using disks, our volume was equal to the integral from a to b of pi r of x squared dx, or r of y squared dy, same thing. If we were doing washers, it was the integral from a to b of pi times r of x squared minus little r of x squared dx, or dy's if you were using y's. And then for cylindrical shells, the volume was equal to the integral from a to b of 2 pi r of x, or r of y, times y times dx.
Okay.
Diameter times height times our width. Now notice that that's cylindrical shells when we're going in the x direction. Just let me rewrite this formula real quick if we were going in the y direction, so that you understand how to make all your substitutions. If we were going in the y direction, v would be the integral from a to b of 2 pi, the radius, at a given y, times x times dy. Because in that case, x would be our height.
Yep, that makes sense.
So those are the 4 formulas that we've been covering today. They have 2 more examples using cylindrical shells, and then we're done. Which, this is taking a lot more time than I thought it would. So, next example. The region bounded by the curve y equals the square root of x. The x-axis, y equals the square root of x, the x-axis, and the line, x equals 4. And what are we revolving around? Revolved about the y-axis. Okay. So drawing a picture,
Oh,
I'm not going to be too precise with my picture anymore. Now I think you get what we're talking about. Here's the line, here's 4. So we're revolving this about the y-axis. Taking that, sweeping it out around the y-axis, right? And this is y equals square root of x. So we're talking about this region. Revolved about the y-axis. You with me?
Okay.
did we just do that?
No, we didn't. So I'm going to calculate this volume 2 ways. I'm going to use the dishwasher method and cylindrical shells, and I'm going to do them simultaneously. Hopefully give you a feel for the difference and where one's easier than another. You with me?
Mm-hmm.
So volume, if we use the washer method, the disk washer method, then how is that going to work? I'm going to need to do my radius at a certain y, and I'm going to be adding up in the y direction. So I need to know how high this thing goes up to 2. So if we're doing the dishwasher method, it's going to be the outer radius minus the inner radius. My outer radius is always 4, my inner radius is this line, right?
Oh, I see. Okay.
So the volume is going to be the integral from, since we're adding up a bunch of washers in the y direction, we're going in the y 0 to 2, and we're going to be doing pi outer radius squared. The outer radius is always 4. 4 squared minus the inner radius squared, x.
X squared.
Sorry,
Oh, yeah.
we need to solve this really quick for x. Sorry. So x is equal to y squared is also how we would say that, right?
Mm-hmm.
So in terms of y, then the inner radius is going to be y squared is going to be y to the 4.
dy.
And then we have dy. So pi outer radius squared minus inner radius squared dy.
Okay.
Good?
Mm-hmm.
And so we won't solve this yet. That's how we set it up using washers. Now let's set it up using cylindrical shells.
Okay.
So cylindrical shells, at some x, I'm going to take, here's a piece of my shell, I'm going to wrap this around, right?
Mm-hmm.
So now the volume is equal to, I'm going to add up all those shells. We're going to start here, we're going to do the shell that goes around here, the shell that goes around here, the shell that goes around if we start there. So I'm adding up all the shells in the x direction from 0 to 4, and it's going to be 2 pi times the radius of my shell. What's the radius of my shell?
Just x.
Just x. Times, what's the height of my shell?
Just y.
Just y, but this time we want it in terms of x.
Root x.
Root x.
Square root of x dx.
Okay.
So here's the cylindrical shells way. Here's the dishwasher method. Notice that anytime if your cylindrical shells are in terms of x, your washers will always be in terms of y. Similarly, if your washers are in terms of x, your cylindrical shells will be in terms of y. That will always be the case with these problems.
So
They're not inverses of each other. Just
Yeah.
something to notice, because maybe working with the y's is kicking your butt. So maybe, say you're doing the washer way and working with y's is kicking your butt. Maybe it'd be easier to do cylindrical shells and work with the x's.
So it's whatever is convenient.
It's whatever is convenient, always and forever.
Okay.
There isn't, this is the way you should do it. These are both equally valid. Now naturally this one looks easier than this one,
Yeah.
but they're both equally valid. And so we'll do both really quick. So working with this one, what do we get? I'm just going to go ahead and integrate it. So we have pi times 4 squared integrated is going to be 16y minus y to the 5 over 5
Mm-hmm.
evaluated from 0 to 2. Good?
Yeah.
This one, I'm going to pull my 2 pi out. And we're going to have, it's going to be times. Now, x times x to the 1/2 is the same thing as x to the 3/2. So that whole term is just x to the 3/2.
So 2/5 x to the 5 over 2.
And this time evaluated from 0 to 4.
Yeah.
You with me? So let's calculate it. I'll call this V1 and V2 just so that we can keep track of which one we're solving. So V1 is equal to, looking at the top one, we're going to have pi times 32 minus 32/5, which is going to be, if we have 32 and we minus 1/5 of 32, we have 4/5 of 32. So that's going to be 128 pi over 5.
That makes sense.
Just times this by 32 times 4/5 pi. Okay, V2 is going to be equal to now 4, we're plugging in right here. What's the square root of 4?
2,
To the 5
32,
times 2
64,
times 2
128.
pi over 5.
Same thing.
Now, I don't know if one of those was really that much easier than the other. Kind of 6s on that one. The example does cylindrical shells, but I want to make sure you can see the difference between how these two are calculating.
Okay.
All right, last example. I'm debating, I was going to do this last night, but I got busy. I think what I'm going to do is do like a review of your test, and I'll just record it at home and upload the video, where I just go over every test problem,
Okay.
since we don't really have time in class to go over it. And that way I can spend class going over homework problems with you guys.
Do you want to just go over the test problems we got wrong then? So you're not, wasting your time with 20 different problems.
The problem is between the two of you, there's almost a point docked on everything.
Oh, really?
Pretty close to. We could try it that way. We'll try it at the end of class, and if that doesn't work, then we'll figure out if I should just upload a video instead.
Okay.
We'll try. Let's see how long this last example takes. Okay, last example. We have the region bound by y equals x squared in the x-axis. So y equals, not x squared, square root of x. Say one thing and think another. And x equals 4. Did we not just do this? And I'm rotating about the x-axis. Okay.
Oh yeah, we've done
Okay. Wow.
that. We need to do that.
Missed. Okay, so we're taking this region, and we're rotating around the x-axis. So it's going to come back down here, something like that, and give us that whole volume, right? Now we're going to do this method using cylindrical shells. So my shells are going to be, when I cut a shell out of this thing, it's going to be like a cut right here that wraps all the way around to like right here. And that's going to be my cylindrical shell, right?
I'm lost. Isn't
Yeah.
x equal 4 different?
X equal 4. 1, 2, 3, 4. What? X equal 4 is right here.
Is that not y equal 4?
That's x equals 4.
What's the y coordinate right here? What's the x coordinate?
4.
What's the y coordinate here? I don't know. What's the x coordinate?
Okay.
X equals 4. But do you see the shell now? Now I'm talking about this shell.
Yeah.
We're taking this cylinder right here. Doesn't really make sense because I didn't draw 3D, but. You see the shells that we're talking about?
Yeah.
So the width of our shells goes in which direction?
Y.
The y. So we're integrating into y.
Okay.
If we use the cylindrical shells method. We could have used the disk method. We could have used shell method. Doesn't matter. In this case, we're using shell method. Should we do both simultaneously again? Does that help? Or should we just do washer, or just do cylindrical shells?
Let's do them both.
Do them both?
How do you
Okay.
wash?
We call it the dishwasher method because disk is a washer where the inner radius is 0. So when I say washer, I could just mean disk. In this case, it's just disks, right? And you can add up all the disks like this.
Yeah.
So let's set up how we would set it up doing it the disk way. We do the integral from 0 to 4, right?
Mm-hmm.
Of pi r squared. R is y. It's just the height at a point. So pi y squared dx.
Gotcha.
Pi r squared dx, add them all up from 0 to 4, that gives you the volume. Okay, cylindrical shells method now, we're going in the y direction. So we're going to do the integral from 0 to 2 now, right? Of, for a shell, it's the circumference times the height times the width we're using. So circumference times height.
So it's 2 pi times,
So we have 2 pi times, what is my radius for one of my shells?
y.
It's just y. So 2 pi y, yeah, 2 pi r, so 2 pi y, there's my circumference times the height of one of my shells. What's the height of one of my shells?
The height of one of your shells?
Yeah, what's the height of a shell? Here's one shell, what's this distance right here? What's that height?
4 minus x.
4 minus x.
That's, oh, because we're thinking the opposite. Gotcha.
So 4 minus x. And we're adding up in the dy direction. So I need to rewrite that x in terms of y. So rather than x, what do I write here?
Y squared.
Y squared. Perfect. Okay, so here's our two integrals.
One's way easier than the other.
One's a lot easier than the other one. So stick with this bottom integral for a second. This is the integral from 0 to 2. Pull out constants, pull out constants. Sorry. Pull out my 2 pi first. 2 pi, there she is. Okay, integral from 0 to 2 of 4y minus y cubed dy. Okay, now we'll solve these integrals. So this integral is equal to pi times x squared over 2 evaluated from 0 to 4. Okay, that's easy as can be. What's our answer there?
8. 8 pi.
8 pi. Yeah, I'm pretty sure we did that. Anyways, now let's work with this integral. When we calculate the integral of this thing, what do we get? Still have our 2 pi out here. 2 pi times
2y.
2y squared.
Y to the 4 over 4.
And this time we're evaluating from 0 to 2. So that's going to be 2 pi times
8. Right?
Yeah, 8
times 4.
Oh, did you just figure out the whole thing?
No.
We're plugging in 2.
We should end up
8.
with
Whoa,
yeah.
thank you. I don't know what my head was thinking. 8 minus
32 over 4. 16 over 4.
So that's equal to 8 pi.
Yeah.
Same thing.
Yep.
One just took.
Again, doesn't matter which way you do it. Just keep in mind that if cylindrical shells is making you integrate with x's, the dishwasher method is going to make you integrate with y's, and vice versa.
Yeah.
So if you're going from one to the other, that better at least happen. And that's something to keep in mind because maybe working with the x's is a pain, so working with y's would be easier, and vice versa. Good?
Yeah.
Okay, so that was the next two sections. Start your homework for those. Feel free to text me over the break with any questions you have. That's perfectly fine. I assume you guys don't have choir practice, so we can meet for
No.
We do.
Oh, you do?